So today we're going to be talking about parabolas in their vertex form and their applications. We're going to interpret the characteristics of a parabola in its vertex form and look at some applications. It may not be so obvious, but when you look at these three equations, they're actually the exact same. This first one is known as a quadratic equation in standard form, and we've seen it before when we were looking at factoring. And this last one is a quadratic function in factored form. And we're going to be working with that later on. But the one we're going to be focusing on today is this middle one right here. And it's a quadratic equation in vertex form. And this is really helpful for us because we're going to be looking at how to find a vertex, and that's actually our best option in trying to locate a vertex. So let's work on that one for now. So just as a little recap of our transformations that we've been looking at for the last little while, we have our stretch factor, which is A. If it's negative, it also tells you that there's a vertical flip. And if it's greater than 1, it tells you that it's a vertical stretch. If it's between 0 and 1, so it's a fraction, then it's a vertical compression. And then we have our d value, which remember x lies. So it's going to be going the opposite direction that you would assume, but it's a horizontal translation. So it's going right and left. And then our c value is going to be our vertical translation. So this one's pretty straightforward. It's going up and down. So just looking at all our transformations here, we can already see that the A factor doesn't really affect, it affects the shape of the parabola, but it doesn't really affect the origin and where it's moving to. So really our vertex is going to be DC, since D is the x-coordinate transformation or shift in the x-axis, and then C is the vertical translation. So our vertex is point DC. Okay, so let's do some examples together. So example 1, write an equation for the parabola with a vertex at -3, 4, opening downwards, and with a vertical stretch by a factor of 2. All right, so for here, we know that we're going to write it in standard form. And so we know it's a vertical flip, right? So it's reflected over the x-axis because it is pointing downwards. So we know we have to have a negative a value. And we also know the stretch factor is 2. So that's our a value. And then we have our point, our vertex, which is -3. The x value is -3. And remember, x lies, so it's going to be x plus 3 in the equation. And this is attached to the x because it's your your horizontal shift. And then you know your y coordinate is 4, and so it's going to be plus 4. All right, for our second example, we have the graph of x squared, which is the parent function, is compressed vertically by a factor of 1/5, then translated 2 units to the left. Write the equation and the mapping notation. All right, so we're going to write our mapping notation first because we're given specific instructions on what's happening. I'm going to tone it down with the pen here so it's not so bold. So our mapping notation is going to be, our vertical compression is affecting the y, but we have 2 units translated to the left. So that's going to give us x minus 2. Remember, this is the mapping formula, not the equation. And we said it's going to be compressed by a 1/5. And so that's our mapping formula. And our equation is going to be y is equal to 1/5, right? That's our a value. And then x plus 2 squared. And we don't have any vertical translation, so we don't really need a c value. Okay, so for this example, we have to write an equation for the following parabola. So we're given the vertex, which is really helpful, and we can write what we know so far in vertex form. So we don't know our a value, but we do know that the x and y coordinates are going to be x minus 6, right, squared, minus 7. So that translates to a vertex of 6, -7, which is correct. So we want to figure out our a value, but we are given this point right here. So 4, 13. And if you remember, just like you did in grade 9, if you want to find the variable a, because that's what we need, we have x and y are kind of like placeholders, so we're going to use any point on the graph to be able to find a. So we have our point for 13. So let's use it. So y is going to be 13, and x is going to be 4. And now we're going to solve it. Okay, so remember your bedmass rules here. So it's going to be 13 plus 7 is equal to 4a. And then we get 20 is equal to 4a. And so a is going to be 20 divided by 4, which is 5. And so our final equation is going to be y is equal to 5 x minus 6 squared minus 7. Okay, so now let's look at some application problems. We have our first example. The path of a soccer ball is modeled by the relation h is equal to -1/6 d minus 28 squared plus 49, where d is the horizontal distance in meters after it was kicked, and h is the height in meters above the ground. Sketch the path of the soccer ball. Okay, so let's draw a little diagram of what's happening here. Okay, so excuse my asymmetrical parabola here. It's supposed to be perfectly symmetrical. So here we have our d, which is our horizontal distance, h is our vertical distance, and we also know the vertex, right? So we know the vertex is going to be 28, 49, based on the equation. And if you look at the a value, it's negative, and you can tell that there's some kind of vertical compression. And so you know it's opening down because we have a negative a value. So first question asks, what is the maximum height of the ball? And so right away we can see that the vertex, the vertical displacement is going to be 49, and so it's going to be 49 meters. Part C asks, what is the horizontal distance when this occurs? And that's going to be at the vertex as well. So that's really 28 meters. So part D asks, what is the height of the ball at a horizontal distance of 20 meters? So really what this is asking is at 20 meters, when D is 20 meters, so at this point right here, what is the H value? So the way to do this is just like you would in any other equation. You're going to sub in D as 20 and solve for H. So let's go ahead and do that. Okay, so here, don't get freaked out. I just found a common denominator, and I get h is equal to 720 over 16, which comes out to 45. So this point right here is going to be 20, 45. All right, so part E says find another horizontal distance where the ball is at the same height as in part D. So what we're looking for here is the x-coordinate now, when, like, let's say that's the same vertical height. When it's, so we're looking for D when h is equal to 45. So the way to do this is we're going to sub in 45 for h and solve for D. All right, so doing that, we have 45 is equal to -1/16. And then we want to solve for D, so D minus 28 squared plus 49. So my first step is to bring the 49 over to the other side. Next step is to multiply both sides by -16. And then remember, we get a positive value because 4 times 16 is 64, or -4 times -16 is 64. And now we have this whole expression on the right side is squared. So we want to undo that square. And so we're going to have to take the square root of both sides. So when we do that, we're going to get this. Okay, so the key thing to remember here is that when we're taking the square root of any number, we're going to get two options. So square root of 64 is plus or minus 8. And then the square root of d minus 28 squared is just going to be d minus 28, right? Okay, so now we're going to have two options. And so we're going to evaluate it when it's positive 8 and then when it's negative 8. So our first option, let's look at when it's positive 8. So we have 8 is equal to d minus 28. And then we're going to bring the 28 over to the other side. So we get d is equal to 8 plus 28. And that is equal to 36. So that is one of our options. And now let's look at the other option. So option 2 is going to be when we're looking at negative 8 and d minus 28. So now d is going to be negative 8 plus 28, which is equal to 20. Okay, so that's another option. Okay, so we were expecting that because if we look back up at our drawing up here, we could see that at this height we have two answers. And so our first answer is when this is 20, 45, and our second answer is when it's, I guess this value is going to be 36, 45. And so the one that we're looking for is right here, which is going to be 36, 45. Because we already had that first value. Okay, so for our last example, a baseball is batted at a height of 1 meter above the ground, and it reaches a maximum height of 33 meters at a horizontal distance of 4 meters. All right, so based on what we have here, we can already see what our vertex is. So our vertex is going to be 433. And we're going to use our vertex form equation to find the equation of the model for this path. And so we have x minus h, which in this case is going to be minus 4 squared plus 33. Okay, so we need more information. We need a point on this graph, and we actually have one because you know that on the path is where he starts batting. So that point right here, so he's batting at a height of really that point is 0, 1, because that's where he's starting. And so that's going to be a point on the graph. And so let's use that to find a, just like we did before. And so our y value is going to be 1. A is going to be what we're going to solve for. And then we get 0 minus 4 squared plus 33. Okay, so then we get 1 is equal to a, so 4 squared is just, or negative 4 squared is just 16 plus 33. Really important to remember your bed mass here, or order of operations. So our next step is 1 minus 33 is equal to 16a. And so negative 32 is equal to 16a, and a is equal to negative 2. And so the equation of this path is going to be y is equal to negative 2, x minus 4 squared plus 33. All right, part B says, what is the height of the baseball once it has traveled a horizontal distance of 6 meters? So if the horizontal distance is 6 meters, we know that's going to be our x value, which is going to be our d value. And so we're going to sub that in. And we have negative 2, so it's going to be 6 minus 4 squared plus 33. Okay, so let's solve that, and then we get negative 2. Negative 2 squared is just 4 plus 33. Remember your order of operations, so we get negative 8. Okay, I'll write it. Plus 33, which is 25. And then, so the height of the baseball, once it traveled 6 meters, is going to be 25 meters. Okay, part C asks, at what other horizontal distance is the baseball at the same height as in B? So we've seen this before. We're going to find the other y coordinate or the other x coordinate when y is at a certain height. When y is 25 meters. So just to mix things up, I'm going to show you another way to solve for this. So we could definitely do it the way we solved it before, but I'm going to kind of use a graphical model to graph this. And so we have something like this. This is a really rough sketch of the path. And we know the vertex is going to be 4. And up here, it's going to be 33. Okay, so let's say this is 25. So this is the point we have, or sorry, this is a point we want, but we have this point, right? So this is the point we found. This was 6, and it was, 625. And so you can say, hold on, let me switch colors here so it's just more visible. So you know that your axis of symmetry here is equal to x equals 4, right? And we also know that a parabola has perfect symmetry. And so here we know that like 6 minus 4 is equal to 2. And so this point is going to be 2 units to the right of the axis of symmetry. So we know that this point right here has to be 2 units to the left. And so this must be 2. And so just based on the symmetry of a parabola, we could solve this. And we can say that this point right here is going to be 225. All right, that's it. See you next time.